So I'm John Hengeveld. I'm the Director of HPC Marketing for the Technical Computing Group at Intel, and I'm real excited to be here today. I've been exploring big data as a strategic topic for a couple of years now. And one of the things that I've come around to lately in looking at big data use cases is the size of the data doesn't define big data. And so I want to start with the notion that big data, I love the phrase big data. It's got that adjective noun form that we just love, like hairy monster or atomic bomb. It sort of catalyzes emotional response. But I'm going to start calling it, I don't care how big data. And I'll start to talk a little bit as to why. You've seen lots of examples today of for these two guys on just where we're going in science and engineering with technology. Technical computing has a lot of scope. There's a lot of insight to be derived from the use of information, both computation and the raw information that goes into it. We struggle to define the limits of big data. You see this model of volume, velocity, variety, and value a lot. And in the old view, it's gigabytes to terabytes. In the new view, it's petabytes and beyond. But does the amount of data matter? Velocity, it goes from batch processing to real-time data analytics. Well, that certainly matters. If we're not taking advantage of the wealth of data fast, the wealth of data that's out there overwhelms us. We're going from centralized structured databases to distributed unstructured multi-format data. Well, that's another I don't care. I don't care how it's formatted. I want to take advantage of the data. So what we're doing is we're removing limits to how we utilize information so we can use it large and small, structured and unstructured, all in the same breath. The technology of big data is a barrier removal. It puts X's in things. I don't care about the structure. I don't care about the size. Ultimately, it's about deriving value. In value, in the olden world, the data was an end in and of itself. How much money did I make this quarter? Or even a lot of the Hadoop stuff today is ultimately derived around search, where the data record itself is material quantity. In the big data world, insight is derived from the data. What's the cancer cure? What's the treatment for the person? How do we make sure that the person in the medical system is given the correct therapy for what they're trying to do? Or how do we make sure that we find the unusual traffic that's going on to study gang behavior or something like that? But the struggle to define big data is not that dissimilar from the struggle to define high-performance computing. We struggle to find high-performance computing because when does a computational requirement become high performance? What's the boundary? We struggle with this because the canonical definitions ignore time. High-performance computing isn't about how big the problem is or how many flops you put on a problem. An exascale today is a huge system, right? You could build it, but it would be massive. It wouldn't be worth the building. An exascale 10 years from now is probably not intellectually huge. It's comprehensively, there's hundreds of them maybe around the world in 10 years. The definition of size is a function of time. So HPC is defined not only by the processing, but by the fact that the processing is connected together to work on a large problem seamlessly. And that, I think, is a definitional element that doesn't go away. When you get to exascale, when exascale is the #1 system in the world, it's the interconnect that defines the exascale. When you get to zettascale, it's the interconnect that defines the zettascale. The tokens are bigger and bigger and bigger, but you still have the challenge of interconnecting these tokens together to make high-performance computing relevant. It's the interconnection, it's the fabric that's essential to HPC nature. In the same way, what's big tomorrow in big data? I don't care how big data. Does big data have anything to do with the size or structure of the data? We struggle to define the opportunity because it's an irrelevant attribute of the storage architecture. More important than how big is where is the data, what does it mean, and how do we reach it? It's the interconnect that's essential. Let me just give you sort of, I have to write this down so I say it correct. I don't care how big the data is because the data is being aggregated, it's being ingested, it's being understood by an intelligence someplace in the system. And you two guys have exactly that model. And that is done before it is analyzed computationally. Before you seek to extract meaning from it, you have to go through a process of ingesting and aggregating, analyzing, and ultimately understanding its meaning. Then you can extract some value to it. So it's not about bigness. It's about what you have to do to it before you turn something out into value. So my definition of big data, and I use this oil field analogy a lot, big data is a class of insight opportunities where the data brought to the problem is multi-sourced, distributed, or such a scale that significant processing is required to drive insight from it. And the example I use is this oil field. And in an oil field, we really don't care that there's oil in there. That's sort of assumed. There's insight in a big data field. The technology of an oil field is how you get insight out of that big data field. The technology in an oil field is the process of extraction. And that's my definition of big data. It's about the process of extraction that defines big data to be. HPC is essential to big data when it's viewed in this perspective. If big data is how you take this massive information, whether it's small, large, structured, or unstructured, and pull it into something that you can use for analysis, then there's four sort of canonical structures, use case classes, where you look at the combination of big data and HPC. You look at data aggregation. This is find a specific group of records that comply with some set of requirements. This is a lot of what you're doing there. And that's somewhat can be addressed by file system applications, but that's not enough. When you add big data to it, you're adding a sieve to that information, process and structure that data. Then you get to data analytics, computation of common characteristics or key regression characteristics on data on top of that. So that's a little bit more complex oil pump where you get the HPC and the file system. And then you get the data visualization, which is constructing a visual representation of a computationally derived model. That's HPC, file system, and visual analytics. And then interactive visualization and simulation. At each one of these levels, you're adding new computational structure on top of a big data architecture that is actually aggregating information for you in service of your analytics. Intel uses big data. Intel uses big data in its process for validating parts. One of our examples is that we looked at a whole lot of data around chip validation processes. And we looked to optimize our chip validation processes, again, this sort of unstructured data for lots of different places, and use that to come up with a faster analytic process for validating results, a streamlined debug process, and how you take this large volumes of historical test data and find out what's unusual or what's anomalous. And in doing so, we think we've contributed to cutting our product time to market by about 25%. There are lots of different areas where HPC and big data collide. The better medical therapies, I actually don't need to go through most of these because you guys have already covered them, which makes this faster. How to find the fastest route through traffic, for example. If I was to take a city and re-simulate the city based on a change in its infrastructure, and then use the raw data from big data to process through that simulation, I can now take big data, apply it through the analytics, and actually say what is the impact of this new bypass or this new development on how traffic will behave in the future. So urban planning simulation, route through traffic, improved security as Redeka described, medical therapies as so graph problems, you already covered this a great deal. Analytic problems with data or in a graph structure, like matching genomes to tumors or finding the bomber in the haystack. Some of these graphs are huge. One of the key points I'd like to walk away with is data for compute in big data is, to first order, never where you want it to be from a computationally efficient point of view. You always have to go find it someplace. It's not cacheable comfortably. So the terms that we deal with in HPC, historically, I've been able to put the data where I want it to be. Because there's a quantifiable amount of data, I can put it someplace, I can organize it in the way I want to organize it to make the computation efficient. I don't have that luxury with I don't care size data problems. I have to tolerate the fact that the data is where it is, and I have to build an infrastructure around that data to work. So the data is rarely here, it's rarely low latency to access. And that has an impact to how HPC interacts with it. What can you do with the data? looking at crowdsourcing information, looking at physical modeling, looking at sensing, data assimilation. My good friend Professor Franklin at the AMP lab at Berkeley has a group of people working at a number of examples of use cases of big data, including things like an earthquake warning detector that goes on your cell phone. You can use all the accelerometers of all the cell phones in the area and actually generate some processing on it so that your cell phone beeps off and says, get a duck and cover. An earthquake wave is about to go through. I'm not sure that's relevant in Arizona, but it sure is in California. That's an example of crowdsourcing information, sensing information, data assimilation, physical modeling, all applied to this context. Intel's view of the world. Enabling discovery through big data. Life sciences applications, most applications are single-threaded. Some algorithms have quadratic scaling, so that the needs for larger working data sets actually directly ties to the compute capacity constraints. And databases are distributed and siloed and will probably stay that way. So Intel is working actively with key partners in the healthcare industry and others to work on application code development, improving the infrastructure of code development, improving the architecture. One of the reasons why we look at things like the Intel Xeon Phi product is you want to have multiple architectures express the same instruction set, so the same methodologies ultimately drive, the same development methodologies allow you to realize different performance efficiencies based on your data. So that's one of the key reasons why we've taken that approach. Because algorithms have different levels of scaling, you need innovation in compute and storage and data fluidity, how you move data around. And Intel is now got Hadoop, Apache Hadoop distributions, Lustre, and we do a lot of work on how you manage data in applications. One of the key things to remember is that when you get to big data, the compute-intensive model breaks down. You must have a balanced system. You must have I/O capability. You must have storage capability. You must have interconnect capability. You must have compute that all balance and function together in order to get performance efficiency. Your design point for HPC systems that are deriving off of big data is actually different. Genomics for translational medicine. I don't want to beat into this because he's covered a lot of the topic, but genomics on top of the life sciences stuff is really a typical model. You've got the ingestion of large quantities of patient data that goes through a computation of lots of pre-computed correlation information using Hadoop. And a company called NextBio is developing an appliance-like device, they call it an appliance, that actually pulls this information together to allow you to do relationships between genomic information in order to try and figure out, one, how to do genomic processing cheap, but two, how to do correlations between data in an effective way, and this is done off of Hadoop and HBase. The processing that's layered on top of this, Dell, for example, is doing some work on developing appliances that look at some of that stuff as well. HPC compute technology, big data. So HPC makes it viable for big data to help change the perspective from batch orientation to mission critical and real time. Because that compute can suck up the information and derive insight for it for large problems. Data moves from the target of static searches to a pipeline of intelligent agents. I think this is one of the fundamental definitional things that will drive forward the next 10 years of big data is the notion that there's intelligence in the pipe that generates the data. And without HPC to compute it on the other end of it, this doesn't do anything for anybody. There's a shift from simple storage architecture to a greater intelligence in the storage system. The need for more compute in the storage to do the work these guys have described is fundamental. Again, the architectural inflection in HPC to respond to big data as a source of information. Cluster computation is still needed for rapid and accurate real-time answers to real-time data. You don't have forever. You don't have 6 months to run a simulation. You have to take this information and do something useful with it now if you're going to catch the terrorist in his act or very soon thereafter, so he hasn't left Boston yet. Fabric performance becomes essential to insight delivery. Again, this notion that the interconnection is a fundamental element of the system design much more than the computation, much more than prior computational models would describe. Whoops. So there is an architectural framework for big data. You have these wealth of sources. Boy, this color is funny. The wealth of sources of data in the world: medical records, social media, log files, surveillance information, genomic data, data location, access, storage, and distribution. This is where the storage layer comes in. Then you have the aggregation, ingestion, integration, and processing capability, a services layer. And then on top of this, you have the categories of the sort of canonical big data analysis applications: aggregation, analytics, modeling, simulation, visualization. Over the next 2 years, you're going to see a lot of change in the way computation is applied to analytics and modeling and simulation. You're going to see a lot of change to the nature of the services that are available, and you're going to see a lot of change in the intelligence that's available in the storage capability. Without that, big data can't be unlocked. So part of what I want to sort of get to you is that there's an architectural change coming. Balance is essential. Balance is essential. And then and this will unlock the capability to deliver value out of big data. So computation of insight from big data, there's a partnership here. Big data, acquiring data and information for analysis and decision making. HPC, analysis, modeling, simulation, information. These two things together are what's going to drive the value of big data. Big data by itself, without the technology of computation, won't get you there. You must have the analytic framework as well. But the analytic architecture changes to meet the need. And with that, my tagline: parallelism's path to the future, Intel is your roadmap. I haven't talked anything about that, but that's not the point. And IDC. Thank you.